Let's ask ourselves a simple question. What is an AHU? The basic function of an AHU is to take in outside air, recondition it, and supply it back to the building. All exhaust air is removed, which creates an acceptable indoor air quality. Depending on the room temperature of the reconditioned air, the fresh air is either heated by a recovery unit, a heating coil, or cooled by a cooling coil. In buildings where a hygienic requirement for air quality is typically lower, some of the air from the rooms can be recirculated via a mixing chamber, and this can result in significant energy savings. A mixing chamber has dampers for controlling the ratio between the return, outside, and exhaust air. Where do you find an AHU? The accuracy of the treatment will depend on the specifics of the project. Offices, schools, swimming pools, laboratories, and factories may require different parameters to be met, as well as level of importance. We're going to take a bit here and just look at the basic types of AHUs. To start, we're going to look at fan and blower coils. When we look at a fan and blower coil, they generally consist of a fan and a heat transfer coil. Simple filter combinations may be incorporated to keep coils clean, as well as removing particulate from the air. Fan coils generally have simple controls and serve as a single temperature zone. They tend to be less efficient than larger AHUs and have difficulty holding tighter temperature and humidity control. The typical differences between a blower coil and a fan coil may consist of filter options in 2 and 4 inch thicknesses, larger coil offerings, electric heat, and possible damper options. Another type of AHU would be a packaged unit. Packaged units are common in smaller buildings and found on rooftops. Packaged units contain fans, coils, filters, and dampers in a single casing, and possibly even include compressors, gas burners, electric heating coils, and heat pump coils. Packaged units tend to treat single temperature zones except for VAV applications. Because of their compactness, packaged units have a lower initial cost. Packaged air handling units warrant extensive maintenance, and changeout could possibly be expensive as well. Over the years, performance and reliability has progressed, and quality can be found now in those units. Packaged units have flow rates from a few thousand CFM to as much as 30,000 CFM. The units tend to be standardized in design, thus limiting the flexible nature of offering an array of sizes to meet expansion opportunities. A third type of AHU would be a modular construction. This modular construction can be identified to the Revolution TFX. Modular AHUs offer flexibility to be more selective in components and sizes. Modules are assembled at the factory or can be shipped individually and assembled on site. They are capable of being segmented or broken down to fit in elevators or through smaller door openings. They are great opportunities for retrofit applications. Many times these units are considered semi-custom units, which carry certified listings over the other custom units in the field. Large industrial AHUs are highly configurable, and construction of the units may include heavier materials, custom coatings, and the capability of being any shape or size needed to fit in special space claims. Many of them can be built and serve the industry for 50 plus years. With all custom characteristics, custom units may take longer to build and cost much more than other AHU offerings. Let's take a look at the system view. Looking over the HVAC system, it is important to note, designing a perfect system is our goal, but building the best system tends to be the result. Change is almost ever present within a building. New customers change over time, their needs and wants change, therefore the building needs some form of flexibility. Perfect today could mean not good enough for tomorrow. Having units with some type of variability or flexibility may lend itself to fitting multiple changes over time. Let's take a minute and look over the basic configurations. Just to revisit what an AHU is doing, air is brought into the unit, passing over the filters through a heat transfer configuration and supplied to the building. Many of those configurations use two methods of supplying air: a draw-through or blow-through design. Let's start with the preheat configuration. Many of you have looked at the last slide and asked, well, why is the heating coil in front of the cooling coil? We see this question from time to time, and note there's no right or wrong to this. This configuration is known as a preheat configuration. The heating coil protects the cooling coil from sub-freezing temperatures. This configuration is typically found in dry and cold climates. The opposite coil configuration is shown with the cooling coil first and the heating coil second. This configuration is known as reheat. The cooling coil subcools the humid air below dew point for dehumidification. Because the air has been cooled so low, a heating coil may be used to bring the air back to a comfortable level. This configuration is typically found in moist, humid climates. In this configuration, an example of 100% outside air being conditioned and supplied to the building is shown. Typically consists of filtration, single or dual coils, and a fan. The next configuration example is of a supply mixed air design. The layout is very similar to the 100% supply air configuration with an added return air duct. This configuration allows outside air to be mixed with return air from the building to meet acceptable air changeover requirements for fresh air. The mixing of the two types of air can aid in lowering the overall energy usage of the AHU that heats or cools the building. Stepping up in complexity, the basic economizer with exhaust uses multiple fans and damper configurations to supply air to the space. With this configuration, a return air fan may pull indoor air from the building and either mix it with outside air or dump the air through a discharge exhaust duct to the outside of the building. This configuration is yet another method of controlling indoor air quality as well as saving on energy cost. Another configuration and a more notable trend in the market is the use of energy recovery wheels within AHUs. An ERV uses site-recovered energy from a building exhaust to precondition outdoor air for temperature and humidity. This dramatically reduces building energy cost. Preconditioning the air reduces the load on the heating and cooling system, reducing energy demand for treating outdoor air by up to 80%. A reduced workload complements energy cost savings and allows downsizing of HVAC equipment for an immediate return on investment. Since we've reviewed the different configurations of the AHUs, let's see what the AHUs are comprised of. Typically, when most people look at an AHU, they consist of a cabinet housing, heating and cooling elements, blowers and fans, and some type of filtration system. But there's also additional items that are included in the units. Dampers, sound attenuators, humidifiers, and UV lighting may become necessary. As we just mentioned in our last configuration, the ERV wheels are a more notable trend in the market. Let's start with cabinets. There are several different cabinet considerations that need to be observed. Cabinet housing ratios of 0.6 to 0.9 yield shorter unit lengths. Sizing in this method provides a variety of cost-effective fan choices by allowing motors to be mounted beside the units within the housing. Overall unit heights may have their place, but in many of those cases, stacked coils and tall doors are typically cost drivers when building a cabinet. More recently, many manufacturers have moved to injection foam cabinet construction, which is extremely rigid. Injected foam insulation with no through metal connections, known as thermal bridging, is available from a variety of manufacturers and generally has a better thermal and acoustical performance than fiberglass insulation. A disadvantage of using fiberglass insulation is having to use heavier gauge sheet metal for structural integrity. Lighter gauge material with foam insulation can meet and or exceed fiberglass insulated walls with heavier gauge metal designs. The need for focusing more on the L240 standard comes into play, where an L is the panel span length and the L240 is the deflection at the panel midpoint. Standards should be written to meet particular deflection requirement, not just a material thickness. Walls that flex create leaks, and for larger units, deeper walls in thicknesses of 2 and 4 inches may be required. to minimize the deflection. Another item to observe is avoiding cabinets wider than 90 inches. Cabinets wider than 90 inches tend to require shipping splits and overwidth shipping charges. Trucks that are 102 inches wide and cabinets wider than 90 inches are likely to have shipping widths wider than 102 inches due to accessories mounted on the exterior of the unit, such as VFDs or disconnects. The width is not the only item to take into consideration on a cabinet. Avoiding cabinets taller than 108 inches is also required. Overheight shipping charges begin when total height is over 120 inches. Total height includes base rails, top dampers, and discharge flanges from different fans within the unit. Let's take a look at the openings to save length. We prefer front and rear fan openings over the top and bottom fan openings. Top and bottom openings add length to the segments. Front and rear openings can be used to save or shorten the overall unit and cut down on cost and serviceability. Since we're talking about overall cabinet sizes, let's just take a minute and look at the overall unit size, which may include tread plate. If a unit only bears a 36-inch height, is it really truly necessary to have tread plate within the unit? Or possibly even a coil section that may require 7 to 10 inches of width? There's no real need or desire to have that tread plate for that particular segment. Stepping to a next item on our list would be the coils. There are several different types of coils available within the units. Those examples can be water, DX, steam, and even glycol. They may also be found in different mounting configurations such as staggered and stacked coils. Staggered coils allow more surface area for cooling and heating, but warrant longer cabinet segments. Stacked coils are often split to allow flexibility in cleaning and changeout. Depending on the tube diameter used within the coils, typical splits of the coils range between 47 and 50 inches in height. On the topic of coils and their applications, let's take a look at a couple of different diameters used within coils. The half-inch tubes are usually less expensive and typically the base starting point for coil design. Selecting chilled water coils with 10,000 CFM or higher allows 5/8-inch tubes more choices in saving cost and potentially saving space within the cabinet. When larger coils use 5/8-inch tubes, it allows for more tubes per circuit without extreme water pressure drop. This may allow fewer coil rows, saving money and space. Another method of saving space and money within coils is selecting coils with higher tubes per circuit. Pushing the water pressure drop to the limit can boost thermal performance and controllability. This may allow you to select a coil with fewer rows and again cut down on the coil depth and cost. When using glycol for freeze protection, use the lowest concentration possible. Glycol reduces heat transfer and increases pressure drop in coils. This requirement can push vendors to use larger coils. We've all been in those applications where corrosion is an ever-present factor. Coils can be found with different coatings depending on the unit location and air being handled. Phenolic and Harrisite is the same thing. Phenolic is a coating generic name and Harrisite is the brand. It's very similar to tissue and Kleenex. A third choice for coating application for coils would be the electrofin process. It typically has the best value and lasts 3 to 5 times longer. Some of the benefits of the coating are no bridging, which can represent some coils within 30 fins per inch up and 16 rows deep. It has a 5,000 plus hour salt spray rating, and it's the only coating that can provide 100% coil coverage. Many times we look at the coil velocities as ever-present items that we need to control within the air handling units. Cooling coils with air velocities above 500 feet per minute is the point where water droplets can leave the outer edge of the fin. This is called moisture carryover. Air handling units should be designed to avoid velocities greater than 500 feet per minute on cooling coil configurations. Heating coils, on the other hand, can run higher velocities since moisture carryover is not present. Many times the heating coils can reach up to 900 feet per minute. DX coils tend to run a little higher than cooling coils, but do have concerns if the airflow velocity is below 350 feet per minute. If space allows, making coil selections larger to reduce velocity, such as 300 to 400 feet per minute readings, allows a small percentage first cost, but saves big in supply fan horsepower over the life of the unit. Tube velocities typically are found between 3 and 6 feet per second, and this reduces the chances of laminar flow within the coil. Now let's take a look at the blowers and fans within the units. There are many types of fans applied to air handlers. The primary differences among them relate to blade configuration, or whether the fan wheel is fully housed or open, and possibly belt or direct driven. 3 different types of wheels may be found in the AHUs: a forward curve design, a backward incline, and a backward incline airfoil design. Fans may be oriented in the AHU as blow-through or draw-through configuration. Draw-through typically is known as the most common installation method in the air handling unit. Since we're on the topic of draw-through and blow-through, let's take a look at this next slide. Air handling units in which the supply fan is installed after the heating and cooling coils is referred to as the draw-through design. A blow-through air handling unit, the supply fan is located prior to the coils. This arrangement allows fan heat, which can be significant at times, to be removed from the airstream without having to subcool the supply air as necessary for draw-through units. Although much less common, blow-through units do have applications, particularly in healthcare where IAQ is very important. We are also starting to see an increase in the use of low-temperature air systems. It is important to properly select centrifugal fans to balance performance and cost. Larger fans are typically more efficient than smaller fans. It is also important to use external static pressure as your driving factor when selecting fans in AHUs. Don't match a competitor's total overall static pressure. Competitors' units have different internal static pressure drop with their components, yielding a different total static pressure on the unit. In this slide, what we're trying to show is the ideal location for fan operation within the units. A good practice is to select a fan with an operating point that is slightly to the right of the peak static efficiency. This is represented by the orange line on the graph. Selecting the fan at 85 to 90% peak static efficiency allows the fan to remain stable even if filters begin to load up. Because we do not want to select the fans to the left of the peak static efficiency, it is also important to not select the fan operating points too far to the right of the peak static efficiency. When done so, the fans are less efficient in operation and may also have more noise issues in the field. Our next topic of discussion will be the indoor air quality. When we look at the indoor air quality, there's many different ways that we can do this. One of the most obvious is the use of filters. Many air handling units are supplied with filters ranging from MERV 1 through 14 in a throwaway configuration, pleated, or bag filter orientation. Many of these filters are available in side, rear, and front loading orientations. UV lights are also used to clean surfaces within the air handling unit. The UV lights keep coils and drain pans clean of contaminants and reduces overall maintenance cost. These types of lights are typically referred to as surface decontamination. Using one or all the methods mentioned will keep coils clean, meaning less pressure drop and lower fan power requirements. Another form of UV protection is called airborne inactivation. Ultraviolet light in the C spectrum is energy-rich light with a wavelength of 200 to 400 nanometers. UV light is very versatile and can be used in disinfecting water, destroying harmful microorganisms on surfaces, or used on liquids and even the air. High-intensity arrangements can control airborne contaminants, including bacteria and mold spores. It has been found that with UV technology and the use of filters, it is possible to destroy more than 99.99% of all pathogens within seconds. Let's take a moment and look at some important standards within the units. Initial points of interest within the AHU is how reliable are the performances. Many of the air handling units that are found in the industry are measured in two different methods, AHRI or possibly AMCA. The AHRI standard is for the entire unit itself, whereas AMCA standards apply only to the fan. It is our goal to look at the AHRI ratings for the entire air handling unit on a whole. The more familiar ones would be the AHRI 260, 410, and 430 standards. As mentioned earlier in the presentation, the use of the L240 standard is a better measure of how the overall box is going to perform against leakage. There are other certifications that come into play for ensuring overall performance of an air handling unit, giving you, the contractor and the owner, more confidence in the product. Now we're going to take a moment and look at some of the tendencies and trends within the air handling industry. Although much of the technology in air handling units has remained relatively unchanged over decades, some relatively new components and practices are being incorporated that can be useful in the right application. Let's take, for instance, direct drive fans. Direct drive fans eliminates the drive losses associated with belts and can result in higher efficiency and lower overall noise. Fan arrays are multiple small direct driven units that are used in lieu of a large fan itself. Applied properly, the fan array can reduce the overall space required for the air handling unit while providing redundancy. Depending on the number of fans, they can be controlled in unison by one or more VFDs. Like so many other things related to air handling units, care must be taken when applying a fan array to ensure the goals of the project are being met efficiently as possible. 1, 2, and 4 fan systems provide overwhelming advantages over stacked multi-fan arrays. The need for full fan redundancy should be challenged sometimes. Systems should be designed around 1 or 2 fans to maintain peak efficiency, and that housed centrifugal fans should be considered when unit length is available. In designs that require full fan redundancy, 4 fan systems should be used to keep efficiency high while maintaining a full redundancy requirement. The advantages of selecting fewer larger fans and motors will dramatically reduce the life cycle cost of owning and operating the air handling units while maximizing the system uptime. Some of the advantages to using larger fans over the smaller array configuration may include lower installed cost, lower energy operating cost, a yearly maintenance cost, reduced electrical service to air handling units due to lower motor horsepower requirements, and may also reduce maintenance costs and improved reliability and uptime. Let's take a minute and look at a couple other configurations or build designs within the air handling unit. For instance, the energy recovery. There are 2 types of wheels, an enthalpy and sensible wheel configuration. Enthalpy is the total energy transfer, which is the humidity and temperature of the airstream, where sensible is only the heat that is transferred. The humidity is unchanged. Energy recovery is increasingly applied in air handling units and may be required by energy codes in certain applications having high percentages of outdoor air. Energy recovery enables incoming air to exchange heat and moisture with building exhaust air via desiccant coated wheels. Successful applications is dependent on many factors, most importantly climate. It is generally easiest and most cost-effective to apply when dedicated outside air units are used. Which brings up the important second feature of this slide. For many climates, the toughest part of an air handling unit's job is treating outdoor air. Coils must be sized to handle the most extreme ambient temperatures. In humid climates, dehumidification requires air to be cooled below the mixed air's dew point, even if the occupancy of the building might not require such a low temperature. Additionally, mixing dampers and their associated control sequences in air handling units are common modes of failure, which together with sensor drift can result in overventilation, known as higher energy use, or underventilation, known as poor indoor air quality. A better approach for many buildings is consolidating all the outdoor air treatment into a dedicated air handling unit that will supply 100% outdoor air. Treated air from these units can be supplied directly to occupied spaces and can be injected into mixing boxes into other air handling units dedicated for temperature control. While the addition of a dedicated outdoor air handling unit might first sound a far more expensive approach, their use may add little to the overall cost of the job, and they can allow simplification of the air handling unit. Now that we've taken a look at the air handling unit and some of the trends and characteristics and installation configurations, let's just take a moment and take a look at the overall Revolution TFX unit offered by Titus. Let's start with a basic overview of the Revolution unit. It's found indoors. It handles between 2,000 and 30,000 CFM. It's available in 36 different cabinet sizes. It's modular in design, which allows us to have 34 different segment options available. It comes in 2-inch foam injected panels. It has some material flexibility, such as stainless steel panels. It also has a competitive leakage and deflection standard, and their quick ship options for semi-custom configurations is available. Just to kind of sum it up and put it all in a tabled format for you, we decided to show the CFM breakout, the cabinet sizes, the notation for the walls, leakage, deflection, and the ratings that are found on all the Titus Revolution units. Earlier I'd mentioned there was 34 different segments found within the Revolution unit. On this slide, I've broken out each one of the segments with their corresponding description and their code. I wanted to take a minute to just show you the overall lead times. Though semi-custom, the Revolution product has the ability to meet different lead times and requirements, especially when it comes to rapid and quick ship requests. I'd like to state that the preceding information was general and is no way a comprehensive guide to proper selection and application of the air handling units. Every project has a unique set of criteria which must be balanced to arrive at the best, not perfect, but best solution. Engineers will organize these criteria early in the project, and a thorough analysis is usually required to support the final decision. Each individual component within the air handling unit must be selected with a combination of research, analysis, and experience. By keeping energy efficiency and serviceability firmly in mind throughout the selection process, it is less likely there will be regrets when the project is complete. Even the best AHUs and installations, however, require a strong commitment from the building operators and owners to keep them running well. Preventative maintenance programs, together with continuous commissioning, will help ensure the lowest possible ownership cost for any system.